So last week we sort of did a really rough and ready introduction to AI, to sort of ideas behind it, to the positives, the negatives, and today we're really starting our work. This is going to be our last session, which I do most of the speaking and talking, okay? So starting next week, the work transitions to your side of the table, okay? So today's lesson, again, is mostly introductory. It's about sort of the fundamental issues that we need to consider when we come to evaluate AI systems, right? So that's why it's more of an introductory course, and I'll be doing a lot more of the talking. And starting next week, we're going to take the basis that we put today, and we're going to start applying those to the different fields of interest, different domains in society. And as we went over the course overview last week, you guys know more or less what I'm talking about. Appreciate those examples. And today what we're going to be looking at is, as I said before, it's really a fundamental issue in AI. It's the basis for every kind of AI system when we come to evaluate it, to assess it, and that's algorithmic decision making. That's the topic for today. And so we'll take a deep dive into that. What we're going to be looking at today are three main issues. We're going to talk about rational decision making. What does that mean when it comes to humans? Are we rational beings? How can we be rational? Why is that an important issue? Then we'll talk about in AI systems. Are we designing these systems to be rational? And when we do so, what is this idea of algorithmic bias? Maybe you've heard of that, right? It's one of these fears that we have, that the systems will be somehow biased. We'll talk a lot about that. And then finally, we'll take a deep dive into this idea of the alignment problem. And this is the question, well, we'll get to it soon, about can we overcome algorithmic bias? Can we make AI systems align and act in a way that we want them to? All right, so this is sort of our goal for today. We're going to try and get through these three things. We'll see how far we get, but I don't think it'll be too difficult. Okay, rational decision making. It's a good question. It's an interesting topic. This was the main topic of my dissertation, so I feel quite comfortable discussing this issue. But we'll see how it works with AI. I never focused on that. So let's see what the differences are. So first of all, what is rationality? That's sort of the basic question we need to be asking ourselves. Does anyone have an idea? When we think about rationality from a philosophical standpoint, there are two main theories of rationality that sort of live within the literature, and we're going to be focusing on both of them really slightly, but the first group of theories are known as coherent-based accounts. And the idea of a coherent-based account of rationality means that in order for us to be rational, we have to have some kind of criteria for coherence within our decisions. They have to come together in some kind of way that makes sense. Now, this leads to a few different kinds of criteria. We're going to look at one or two of them as examples, right? But before that, let's just see sort of what the implication of a coherence-based account is. And this is by John Broome, who's an Oxford philosopher, well known in the field, an economist and philosopher. And he writes that it seems that a coherence-based account of rationality, right, is a conceptual feature of rationality that it depends only on the mind. Now, what does he mean by only on the mind? Well, the idea is that in order for us to be rational, only the internal states matter, right? So coherence-based account of rationality means that it is a question of how we make decisions, regardless of what's going on outside. We just need the internal state to make sense, to cohere to one another. And let's see one example of that. One of these core principles of rationality that come about. And one of these examples, and this is a famous joke in philosophy that came out by Larry Temkin, and Temkin says that, well, John goes into an ice cream store and tells the server, I'll have strawberry, unless you have vanilla, in which case I'll have chocolate. So what's the idea here, right? There's something wrong, something's weird. What is weird about his statement? Can anyone notice that? So what we're seeing here, this is known later as the principle of irrelevant alternatives, but that doesn't matter for our case, right? What matters is that, well, if you want to have strawberry because you prefer it over vanilla, chocolate has nothing to do with this situation, right? And again, these are internal features. It's our beliefs and how they come together and cohere, okay? So Larry Temkin gave this really, really nice joke. And as I said in the first session, all these pictures that I'm generating here are usually image-based, generated by Midjourney, or they changed their name recently to Muse something. And these are the prompts I give it. So maybe take a peek. Sometimes the prompts have nothing at all to do with the picture. It's very fun to see the contrast, right? So the example here, I wrote chocolate, vanilla, and strawberry ice cream at an ice cream store. And this is what I got. So that's pretty good. Not bad, right? I got the 3 correct colors. It seems properly. Okay, good image. And we'll see, we're talking today about algorithmic bias. And we'll see how prompts have to do with biases. We'll talk about that soon. Okay, so that's sort of the idea of coherence. Now let's take it to the extreme. Now, I grew up watching the Star Wars movies. I don't know about you guys. I think I'm a bit older than most of the people here, not by much. But this was sort of my childhood. And whoever grew up watching Star Wars knows that there's a very strange fact about the Star Wars trilogy. And that is that if we compare the 3 movies, A New Hope was clearly better than Empire. That's a well-known fact. And that Empire was better than Return of the Jedi. Everyone knows that. And the weird fact is that Return of the Jedi was way better than A New Hope. Okay? And this was sort of a well-known fact. And what is the problem here? We're seeing something known as a cyclic preference ordering, right? So A is better than B, B is better than C, but C is better than A. And what is the problem with these types of cyclic orderings? Now let me take you through a short thought experiment that reveals why this is a problem of rationality. So imagine that you are going to see a movie, you're entering the cinema, and the option you chose is A New Hope. You have a ticket, you're excited, you already have the popcorn, you're getting ready to go in. Very nice. And someone comes up to you and says, well, you know, I could switch the movie for you. I'll give you Return of the Jedi instead if you just pay me $1. Now, because your preferences are clear, you prefer Return of the Jedi over A New Hope, right? You prefer it. Right here, see? So you agree to the swap. You give the $1 and you get a better movie to watch. Excellent. Until here, you're satisfied. You get your popcorn, you're ready to go in. Your friend is smart. He says to you, wait a minute. I actually know that you prefer Empire Strikes Back to Return of the Jedi. Give me $1 and I'll switch the movies for you. You'll get what you like and everything's good. Okay, you agree again. But then your clever friend tells you finally, well, you know, I know that you actually prefer A New Hope to Empire Strikes Back. Give me just $1 single and I'll switch the movies for you. And so what happens is you end up exactly where you started, only you're $3 a bit shorter in your pocket. And this cycle can go on and on and on and on and on and on and on. And this is what is known as a money pump, right? When your preferences are transitively ordered, you become a money pump and you can be exploited. And that's why we say that it is incoherent, it is irrational to have a cyclic preference ordering. And that's why coherence-based rationality shows us that in order to be rational, our preferences have to be coherent with each other. We need to avoid money pump situations by creating transitive preference orderings, right? So if I prefer A to B and B to C, I have to prefer A to C. I can't prefer C to A, right? That's a non-cyclic preference ordering. And that's sort of an account of rationality and coherence reveals that to us. Okay, let's see one more example of the coherence-based account of rationality. And here we're going to go to the world of the Smurfs, which I love using as examples. Now, first of all, we have here Smurfette. Now, again, generated by Midjourney, I asked Midjourney to give me Smurfette using her hands as a balancing weight, as if considering a problem. So I wanted Smurfette to be something like this, right? Well, this is what I got instead, but okay, close enough maybe. Now let's imagine Smurfette knows that there's a flu going on, okay? And she does not want to get sick. And she heard from her neighbor, Vanity Smurf, that this flu is not dangerous at all. You have nothing to worry about. No one is getting sick. Everything is good. She feels good with herself. There's a flu. It's not dangerous. I have good evidence. Perfect. Fine. And Vanity Smurf. Again, I got Vanity Smurf looking in the mirror. Okay, that's maybe okay. Although all these wrinkles, I don't know, but whatever. But then Smurfette talks to her other friend. That's a Brainy Smurf, okay? And Brainy Smurf, a Smurf dressed as a doctor looking especially wise and smart. And that's the image I got. And Brainy Smurf tells her, well, you know, Smurfette, this flu is actually quite dangerous. Okay? This flu can really get you sick. You know, some people are even getting vaccinated for it. Now Smurfette has contradictory evidence, right? She has evidence from Vanity Smurf that the flu is not dangerous. She has evidence from Dr. Smurf or Brainy Smurf that the flu is dangerous. What is Smurfette to do? Can she hold both these beliefs at the same time? Obviously not. A coherence-based account of rationality will tell us that we cannot have contradictory beliefs. If we have contradictory beliefs, they're incoherent, we're irrational. And so how do we restore rationality in this case? How do we restore coherence? What do we do? Do we hold both beliefs? Or do we do something else? Maybe we'll get rid of one of them, right? Which one do I get rid of? Vanity Smurfs or Dr. Smurfs? But wait. A coherence-based account tells us it's all internal states. To be rational, I only need coherence. It means I can't have a contradiction. So if I'm a coherence-based account of rationality, it doesn't matter which belief I give up. I can give up either of them, so long as they're coherent. Okay? If I have evidence, regardless if it's good or bad, and it doesn't contradict other evidence I have, I am rational to believe what comes from it. That is the coherence account. The outside world does not matter. Keep that in mind, because this is a strong critique against this account, right? On this account, we can't explain why Smurfette has to believe the doctor, which is our intuition. Okay, this is the first account of coherence. So the second account of coherence, or of rationality, is what is known as a reasons-based account. And this will try and answer this dilemma that we're now dealing with. Okay? A reasons-based account tells us the opposite way, well, not the opposite. It tells us a different way to understand rationality. It tells us that an action is rational if there's a good reason to perform it. And the same for beliefs, right? A belief or a set of beliefs are rational if there are good reasons to believe them. If they're valid, if they're strong, if they're weighty, if they provide us with good evidence, and so forth. The theory of practical rationality is a theory of good reasons for actions. So to be rational means to have good reasons to act. And again, now if we go back to our Smurf case, we would say that Smurfette is not rational by giving up, on the doctor's reason that's provided, because that's not a good, because Vanity Smurf did not provide us with a good reason to believe that the flu is not dangerous. Perhaps he's uneducated, perhaps all he's concerned about is his good looks, right? We have second order evidence that he's not the sharpest pencil in the box, okay? We know that Brainy Smurf is more reliable and so on and so forth. Provides us with a good reason, a better reason, a weightier reason, one would say. Okay, so those are the two accounts we're going to be having them. And take these as heuristics, right? Complex accounts of rationality have to take account of both worlds, right? We saw there are weaknesses in both sides, sort of, right? If I only think of the weight of reasons, you'll see later that there are strong problems with that. And we'll try and flesh those out. And one of the issues is that we can think of rationality in two different ways. We can think of the structure of rationality as being instrumental, right? I think Stefan said to us that it's a question of maximizing your utility, right? That is a sort of an economic notion of rationality. Instrumental rationality takes us from our means, it takes the best means to reach the ends that we want, okay? But the problem with structural rationality, maximizing utility, as we said, is that it doesn't say anything about our ends, right? Our ends can be anything. So if I have to take the best means to reach my ends, and my end is to rob a bank, probably the most rational way to do that is to wear a mask, have a gun, make sure there are no witnesses, and so on and so forth, okay? That's thinking rationally on this instrumental structure, right? And now when we're talking about good reasons, bad reasons, does that play into this account, or is it more a coherence sort of idea? If I want my means to lead to an end, it seems to be a bit closer to the coherent account, right? I want it all to make sense, all to flow together. The goodness, the value of these reasons, irrelevant, right? It's all a question of how to arrive at that. And often when we hear economic analysis or politicians, right, they sort of set aside that whole goodness normative issue, right? They sort of say, well, this is our goal, and this is how we'll reach it, and this is how we achieve it. And when we talk about behavioral economics, that is sort of the paradigm way to think about it, right? Maximizing preferences. Preferences are all that matters. It's regardless, we cannot debate about the ends. In contrast, we have the opposite side, which is what is known as substantive rationality. Substantive rationality tells us that the means-end structure is insufficient because it doesn't raise the ethical moral question of what ought I to do. And this is where sort of normative ethics come in, right? Normative ethics is interested in the ought question. What ought I to do, not as a means to an end, but as in all things considered judgment. Morally speaking, prudentially speaking, and so on and so forth. We have to bring all those together. So when we talk about substantive rationality, we're usually referring to this idea of finding in all things considered judgment. And again, this can relate to both theories of rationality in a sense, but a bit stronger to the reason-based account. because we already insert into our notion of rationality this idea that ends are up for debate. There's a good end, there's a bad end. And you ought not to do a bad end because we're not talking instrumentally anymore. Okay, so keep these in mind. Again, I said use these as heuristics. This is not a course on rationality, so we're just sort of taking a peek at this in order to ask ourselves a question about our session today, which is decision-making, algorithmic and human decision-making. So the big question that now we need to ask, are we rational? Are human beings rational? Okay, so taking all the pieces that you guys said, rationality is a challenge, right? That sometimes we meet and sometimes we don't. It can depend on extrinsic factors. It can depend on our personality, right? So it's not, I get the consensus here is that we are not purely rational creatures and that we might strive for it, but that is a question of effort, it seems. Now let's look at some of those things that might trouble us or come in our way. So we have emotions, right? We can get angry, and when we're angry sometimes we act irrationally, people say, right? You do things at the spur of the moment. You don't consider your options. And again, the prompt here, a person feeling very angry, person. We have time pressure, right? We have something that's known as bounded rationality, rationality within the constraints of what it is that we have. Look at the lovely numbers of this watch. It's a very creative watch. Very interesting. We have what's known as weakness of the will, right? Temptations abound. Here I wanted to see a person considering whether to eat another piece of chocolate, and well, close enough maybe. It's tempting us, right? We are creatures with lust and need and wants and feelings and emotions. And now we're going to test all your rationality. So this is your first opportunity to take part for once. And I have here a small quiz. So everyone take out your phones. And we're going to look at something known as cognitive biases. Okay, now actually these two questions are identical. So both groups actually had the exact same question, only the answers were phrased a bit different. The answers were phrased, one of them in positive and the other in negative. But the answers are the exact same. Okay, and what it shows us that people, whenever they have the option of saving 200 lives, right, versus a 33% chance, who had this question, saves 200 lives, raise your hands. So when this formulation appears of saving lives, 72% tend to choose option A. And when the formulation is in terms of negative, 400 people will die, which is the exact same, 200 saved or 400 die, the exact same, only 22% tend to choose A. So we see a huge flip whether we put it in positive or negative terms. And this is known as a framing bias. This is a classic bias, and we saw that it sort of panned out here also. 80% of the class favored A when it was saved, and here was more split. But maybe if we had a bigger group, it would have shown us these results. And what is the problem here? So we found out, or behavioral scientists have found out that we as humans have certain weaknesses. And those weaknesses in decision making are that extrinsic factors unrelated to the decision itself, how the decision is presented to us, the conditions under which we're making those choices, have a huge impact on what we ultimately choose. Apropos our rational capacities, right? The exact same question, framed a bit different, and we have this huge flip between where our preferences lead us, our intuition pushes us. So this is known as a framing bias. However the question is framed to us tends to push us into one direction or another. And this is well established in research, so you can find a lot of these different questions. And these are all known as cognitive biases. We're going to be looking at a few examples. What are cognitive biases? Imagine that you have this target, and you're aiming at it and you shoot, and you consistently miss the bullseye in the same area. This is an illustration of how cognitive bias works, right? It is that we consistently tend to be skewed in our aiming. It's not sporadic, it means we are systematically skewed. And these cognitive biases sort of reveal those instances in which we are systematically skewed. So let's look at another example. This is known as an anchoring bias. And what the anchoring bias shows us is that people tend to make decisions according to what they saw a little bit before, according to the reference point they have. Now let's look at an example. There was an experiment conducted about coffee buying, and what they did in a cafeteria, they put up two coffee options, a 95-cent coffee and a $1.20 coffee. And they showed that 29% of the people chose the more expensive cup. Okay? So 70% decided to go for the cheaper cup in that case. And when they made a slight change, they made a tiny, tiny change by 5 cents only. They changed now, the cup was $1.25. We see a jump to 56% of people now tended to buy the larger cup. The 5-cent difference made us suddenly think that we're getting better value for our money here. And the anchoring bias here has to do with where the decimal point is. And you know this is a classic selling technique. $2.99, right? We think it's ridiculous. We think it means nothing. Every empirical test of this shows that this has huge impact on what we tend to do. If it's $2.99 or 3.1, it's a complete difference of how we approach the purchase of that product. And this is subconscious, right? It's a bias that we have, an anchoring bias. Car salesmen tend to use this a lot. They'll first show you a really expensive car, 70,000 francs, brand new car. Yeah. Then they'll show you, okay, we also have an option here for 40,000 francs. It doesn't matter whether that's a good purchase or not. You're going to think that you're getting a good deal because you just saw a way more expensive option. So when you go to a dealership, you'll always be offered a more expensive car first to anchor you. Okay. Another example is known as the default bias. What default bias is that we have a tendency not to change the first option we are given if we can't see good reasons to do it. So here there was a huge research about organ donation cards, right? Whether I sign up to be an organ donor. And what they found out is that there's a humongous disparity between opt-in and opt-out. So it means if by default I'm not an organ donor and I have to actively go and sign a card, that's an opt-in. Denmark 4%, the Netherlands 27%, United Kingdom 17%, Germany 12%. If I flip the default and I say automatically you're a donor and you can opt out just by signing a ticket. Austria 99%, Belgium 98%, France 99%, Hungary 99%, Poland 99%. Okay, there's no huge difference between these countries culturally, economically, right? More or less European countries, more or less westernized. And we see, look at that disparity. We wouldn't expect such a huge difference between opt-in and opt-out. So this is a default bias, huge impact. Okay, those are just a few examples of cognitive biases, apropos us being rational creatures. And a second area in which our rationality is challenged is known as noise. Noise, unlike bias, remember bias was a systematic error. We aimed always at the wrong spot. Noise is a sporadic error. We're constantly missing the target every time in a different direction. Noise creates changing decisions that are not systematic. So let's see a few examples, and some of them are really ridiculous and scary even. So this is a famous case study that they did about judicial decisions. A study looked at 1.5 million judicial decisions over 3 decades and found that judges are more severe on days that follow a loss by the local city's football team than they are on days that follow a win. Completely unrelated to the facts. If you were lucky and the judge's team won, he's going to give you a lighter sentence. This is called noise. It's irrelevant to the decision and it makes sporadic sort of choices. Another noise in judicial decision making that was found out is that sentencing changes drastically before and after lunchtime. If the judge is hungry, he'll choose one way. If he just ate a good meal, choose a different way. Completely, we wouldn't want that to be, and yet statistics show that it is. Another example, I spoke about this last week. Highly trained specialist psychiatrists under study conditions were only able to agree that a patient has depression between 4 and 50% of the time. We have a lot of disagreement, a lot of change between specialists in the exact same field. They cannot cohere to a single set of rules in diagnosis in psychiatry. And here's another really incredible statistic about forensic science. We think forensic science is an accurate thing in which there should be 100% accuracy. After all, people go to jail for fingerprints on a weapon or on a door, right? And yet we find that noise infiltrates forensic science quite significantly. Here are some statistics that came out of a study. When people correctly identified a fingerprint and then re-examined it later, there was an excellent success rate. 95% could, on the second time, correctly identify whether that fingerprint is a match or not. That still leaves 5% error, okay, which may shock some people. But here's the more serious stuff. When they had an erroneous identification in the past, and then 6 months later they were given the same exact fingerprint to assess, 31% now were able to identify it correctly. So 31% changed. 56% did not repeat their error. That means 56% of the people in the study managed this time to exclude the fingerprint, to say that it was a false match. So we're seeing changes, drastic changes between forensic science that have, in the end, life or death situation, or not life or death, but imprisonment at least, situation. And the same thing for exclusion and inconclusive. We see drastic changes. And this was a huge hit to the validity of these types of evidence in courtrooms. And there's a lot of studies going on as to how can we change this option. Maybe we should use certain kinds of automated systems to do it, right? So all the idea of talking about these cognitive biases, these noise, is to show that as human beings in decision making, we are quite fallible, right? We are very often emotional, angry, right? We tend to be tricked by how things are framed. We have time pressure. We have weakness of the will. We change according to these anchoring effects. And we are often noisy and biased. All these issues are the fallacies of human decision makers. And so you can see why there's a huge temptation to say, let's get rid of all of that. Let's try and overcome that by science, by technology, by using AI systems. And that's the trend today. Right? We talked about all these ideas last week, and we're seeing sort of the justification behind it. Right? There is a need to enhance human decision making because it's terrible sometimes. Right? So perhaps relying on AI can be better. And that's sort of the motivation behind that. And now, of course, there's the question, well, how reliable are the AI systems? Do they really succeed in overcoming these problems? And now we're going to be talking about this inherent idea known as algorithmic bias. In order to understand, we talked about biases in humans. Are these the same types of problems that algorithms have, that AI systems have? Or are they a bit different? So let's see. What is an algorithm, first of all? Remember, today is a foundational class. We're trying to create tools for us to assess these technologies and systems over the next coming weeks. So let's start with the basics. What is an algorithm? Well, an algorithm is a set of instructions or steps for solving a problem or completing a task. Algorithms take input data, they process it, and return an output. From this description, a very general description, right, layman's description maybe some would say, is there anything technologically essential about this description? Actually, no. If you look at it, there's no reference to technology. There's no reference necessarily to mathematics or to AI systems. An algorithm, of course, usually we say it's within a computer software, right? But essentially is a way of arriving at a decision. It's a method. It's a method from going from input data to output. And when we use this within a computer system, that is the typical way that we know of algorithms in AI. And sort of we're going to try and understand what are the weaknesses and advantages of algorithmic decision making. And keep in the back of your mind whether as humans we decide algorithmically or not. We talked about rationality, we talked about the fallibility of humans. Do we come to conclusions algorithmically? Or maybe a different way, or maybe sometimes. That's sort of what we have to have in mind. Now let's watch a short video, an introduction to the idea of algorithms. Let's see.
I have a confession. Sometimes, with no one in sight, I code in a white mask. I make whimsical systems to paint walls with our smiles or project inspirations on faces, I enjoy using code to make my ideas a reality. Computer vision powers my creations, making it possible for machines to detect faces. But at times, I'm invisible. You see, machines view the world through a coded gaze. They digest pixels from a camera in dictated ways. Using machine learning, we create training sets with examples that help the machines detect new faces. A lack of diversity in these training sets leads to limited systems that can struggle with faces like mine. To save time, code libraries for facial recognition are shared like off-the-shelf parts. Many computer vision projects share the same code. Any bias in the system propagates widely and implants a coded gaze. The coded gaze reflects the views of whoever creates the systems. All of our work reflects both our aspirations and our limitations. Can we do better? Yes, we can begin by intentionally creating inclusive code. I call this encoding. Encoding is a mindset that asks, who's missing? Detecting the invisible is easier when you have full spectrum teams equipped with different light filters. Who codes matters. Encoding is a process that explicitly checks the impact of bias during the design, development, and deployment of coded systems. How we code matters. Encoding is a personal mission and an invitation to create a world with a culture of inclusion. A world where technology works for all of us and centers social change. No more masks.
Okay. So I recommended watching the movie on the reading list. Has anyone had a chance to see it? Okay, one or two. Really interesting movie about algorithmic bias, about facial recognition software, about how the training data or that these systems were taught and that they used in order to create these softwares, right, failed to notice oftentimes African-American faces or black faces. So darker faces were not detected, lighter faces were. And then it's a whole movie about people being affected by different types of algorithms, right? So today we're going to be talking about algorithmic bias. And that was sort of the introduction to this idea. And let's look at an example. And this is an example I really like. It's a riddle. So let's see if you guys can solve the riddle. A young man is involved in an automobile accident in which his father is killed. Seriously injured, the youth is rushed to the emergency room of a hospital, and the surgeon is called in. Upon entering and seeing the patient, the surgeon exclaims, "Oh my God, I can't possibly operate on my own son." Now the question is, how is this possible? What's going on here? So what this example was sort of given to ChatGPT, right, to try and answer sort of, and let's see what the answer the ChatGPT gave. Well, the surgeon is likely the youth's biological father and was unaware of the relationship until entering the operating room. The situation presents a conflict of interest for the surgeon, as the surgeon's personal relationship to the patient may interfere with the surgeon's professional judgment. Great analysis. This was shown to be quite systematic. It's very hard to get ChatGPT to admit that the surgeon could be the mother. Right? You have to directly confront the chatbot in order for it to think about this option. Right? And what does this example show us? Right? It shows us that ChatGPT has ingested data or has learned that surgeons are a masculine job. Surgeons are males. And so this statistical correlation is stronger than its reasoning capabilities of thinking maybe the mother's going on. The mother is the surgeon here. So instead you have to find creative answers. The biological father didn't know it, maybe they were lovers, and so on and so forth. It gives a variety of really interesting answers. Almost never the answer is the surgeon is the mother. And this is algorithmic bias. A system learns a certain pattern and it reproduces that pattern constantly. In this case, very simple, it reproduced this idea that surgeons are males. And because they're males, it must be the father in this case. Let's see a few more examples. Here we have a famous problem that happened with Google's facial recognition software for mapping out pictures, right? So it categorized these as skyscrapers, airplanes, cars, bikes, gorillas, and graduation. These are not gorillas. But is the AI racist? Is Google Photos, I don't know, does Google Photos hate black people? Well, that would be a weird thing to say, right? Well, an AI system is not a human, right? It doesn't have desires or thoughts, right? The AI system learned that for some reason, a dark face on a moving creature correlates with gorillas. And what was Google's response to this? Did they fix it? Did they retrain the program? No. They removed the tag gorillas. You cannot get Google Photos to tag anything as gorillas. They just removed it from the dataset because they couldn't manage to teach it to stop doing that. Algorithmic bias. Let's look at a funny image generators that recently was sent to me on Twitter. This is about philosophy. So someone was asked, well, one of the image generators was asked to draw me a philosopher. Well, yeah, that looks pretty good. It's a philosopher. Yeah? Well, how about if I ask it to draw me 9 philosophers? Well, okay, they're more than 9. Let's forgive him that, or let's forgive it that. But still, I think we see some kind of pattern about all these philosophers. Is it the beard? Maybe. Is it the glasses? Maybe. I think it's men. And white men. Well, let's see how far that goes. Draw me a philosopher wearing makeup. Well, the philosopher has makeup. The beard had to stay, though. That was important. How about now? Draw me a philosopher getting ready for a girl's night out. It can't lose the beard. Unable to. Draw me a philosopher wearing a skirt. Still doesn't work. Draw me a philosopher getting nails done. I think, therefore I am pretty. It's a nice quote. No? Finally, philosopher on maternity leave. Here we go. Why does the philosopher have the bottle? Where's the baby? That's what they were asking. Unclear. There's another big bottle here also. What do we learn from this? Sorry? Philosophers are men. That's obvious. Philosophers are men. Here you go. Makeup doesn't change its mind. Maternity leave doesn't change its mind. We can force it to make women if we directly ask it. So they manage the continuation of the series. They get it to generate some women. Right? They ask it, I didn't bring those pictures. They ask it to draw a philosopher queen. And it gets it to do it sometimes. So they can get it to do it, but it's quite difficult. There's a default understanding, a statistical correlation between what the system understands is a philosopher and all the other inputs rank lower than that. So when we take these algorithmic biases, what the system has learned, and then we want to translate it into decisions, that's where the problem begins. Not that the first set of examples that I gave are not problematic. They're very problematic, obviously. But we can say, well, this technology is not mature enough, right? This technology isn't ready for use. These are experiments. We can give it excuses, sort of. But once it hits the real world, once we start making decisions based on these systems, we find way more severe problems. So an algorithmic decision is essentially using outputs produced by algorithms to make decisions. Very simple, very easy. Now, in order to see how that works, I want to show you all an example of an algorithm, right? Or this is an architecture known as a neural network. And what we're seeing here, this is the structure of an AI system. And these squares are known as nodes. And all these nodes are hidden from us. And all these lines are how the nodes interconnect to each other. This is the internal system. And what this system learned to do is recognize digits. And let's play with it. Let's test it out, because I have it here in real life. I want us to see together how it works. So here's the algorithm itself, or the neural net. And now let's see how it works for us. So I'm going to start by drawing the number 3. And see, it lights up the number 3. So it says it recognizes that I drew the number 3 through these nodes. Each node represents a way in which the system has been taught to understand different pixels and the pattern of those pixels coming together to lead to the conclusion. And that's why all these interconnections are there. Let's try again. Let's try a different one. Let's do the number 9 this time. And you see, it lit up. Let's try it a bit slower and see at what point it starts to recognize. So I'm going to try the number 2 this time. It thinks it's a 7 now. As I go down, it's starting to flip a bit. Oh, here it thinks it's a 3. And now it knows it's a 2 already. It's convinced that I'm drawing a 2. So you see, you don't need the complete image for it to identify the digit because it's a pattern. And it can rule out certain options. Right? As I get closer and closer to the digit 2, it sort of knows that this is where it's going to be. It can surmise that that's what I'm trying to draw here. Let's do one more example before moving on. Let's try 8. Got it perfect. It's excellent. Wonderful. Now let's do something a bit to try and trick it. Let's see if we can. Let's do something a bit different. Did I draw the number 6? What did I draw? A smiley face. Why does it think it's 6? It's completely certain. It's completely black. It can give me also less black, right? And say, I'm 50% certain that it's this. It sees this smiley face as the number 6. I don't know, maybe. Was that my intention, though? Was it hard for you all to know what I drew here? It was very easy. And this is part of the weakness, and I love this example because it shows that an algorithm is only as good as the outputs it can produce. The output of this algorithm has to be a digit between 0 and 9. It can't be any other way. And so all the world is 0 to 9. It's like what we say about a hammer and nails. You know, often people say that AI is like a hammer and it sees everything as a nail. Because that's what a hammer does. It hits the nail. So everything becomes a nail, regardless if it is. Yes, please.
Can we do it like a 12?
We can try. Let's see what happens. Let's see. So first of all, it recognizes 1. And once I add the 2, so now it thinks it's 2, but not 100%. You see, it wasn't certain. And we can try different handwriting, right? This is not fine-tuned to me. This is a general purpose algorithm, so I just found it online. So it's supposed to recognize any type of handwriting that it has in its data set. Okay, so we saw once I gave it a smiley face, the smiley face disappeared. Remember the coded gaze? The algorithm can only see what it's learned to see. And it can only tell us or reply to us with the outputs it has. Now keep that in mind as we now move on to look at these algorithmic decisions. Our question is always, why did we arrive at that conclusion? Did we arrive at that conclusion? Did the algorithm recommend a certain choice because that's the right choice? Did it recommend it because that's the statistically most relevant option? Did it recommend it because that's one of the outputs that it has only? So how we design these algorithms and these AI systems leads directly to the type of answers we can get. Let's see a few examples. There was a famous incident in Amazon where they developed their very own algorithmic hiring system. They wanted to have a system that would scan through all the CVs that come in and find for them the best candidate for the job. And of course, they spent a lot of money in developing this. It was an in-house project. And then they started running with the algorithm. And it was very quickly discovered that it was biased against women. That somehow it correlated certain types of activities on your CV to be negatively correlated to whether you're a good or bad candidate. And those types of somethings in the CV were like women's chess club, like women's feminist group. Anything that was correlated with a female activity dropped your points in the gaze of the algorithm. And why is that? Why would an algorithm do that? Does it hate women? Do the people at Amazon hate women? Are they bigoted? Well, no, actually what Amazon did is it asked the system, find me the best candidate, and it gave it the data set, all my existing employees. And what can we do? When you look at the data set of employees in Amazon, you see that the higher ups are all men, and those who stay in the job longer are all men. And so the system learned, well, that's what means to be the best employee. Instead of getting a good worker, they recreated the types of workers they already had. The algorithm is only as good as the question we put in front of it. Let's look at another example. This is a famous example that there was a report on this on the COMPASS system. And the COMPASS system is a recommendation system used in the US to advise judges about recidivism scores, about how likely you, as a felon or as an offender, are likely to recommit a crime. Okay? So the system has the questionnaire that is given to the people before the judge. They answer that questionnaire. It's fed into the system, and the system gives them back a score from 0 to 10. Low risk, high risk, how risky is this person? And then the judge can use this in his or her decision as to whether to set bail, whether to keep that person in custody or not. And this is a case that they examined in the report between Vernon Prater and Brisha Borden. Now, Vernon received a score of 3, a low-risk score, and Brisha received a high-risk score of 8. Now, let's look a bit at the facts about Vernon and Brisha. Well, Vernon had 2 armed robbery prior offenses and 1 attempted robbery. Well, Brisha had 4 juvenile misdemeanors. Yet, Brisha received an 8 and Vernon a 3. Subsequently, Vernon was arrested again for grand theft, whereas Brisha never committed another crime. What they found out, what ProPublica, that ran this inquiry, found out was that COMPASS was biased against minorities and specifically against African Americans, against black people. It was biased, and here's the interesting part. There were no racial questions within the form. The system didn't know that it was assessing a black or a white person. And yet what the system did, it created proxies for itself. A proxy is a way to recreate a certain criteria that is out of my learning data or my set of acceptable criteria, and I find a way to arrive at that through an alternative option. In this case, it had a lot to do with postal codes. The system found out that if you live in a specific area in the US, you are way more likely to commit a crime. And it just so happens that all those specific areas were populated by inner city, minorities, low-income society. And so it took that existing data about who commits crimes and recreated it into its assessment. It learned that minorities are more likely to commit crimes, people who live in certain areas are more likely to commit crimes. It calculated that, and it produced here that Vernon, the white thief, armed robber, gets a 3, and Brisha, who stole a bicycle, if I remember correctly, gets an 8. Yeah. Another issue of algorithmic bias that we're not really going to talk about, but we can sort of reference it now when we're talking about sources of algorithmic bias. And the data, that's another issue, right? So you were asking, why does postal code become a significant parameter or criteria? The data that we feed into these systems is enormous, enormous. And we as humans just, it's way, way, way beyond our capabilities of evaluating them. And within these data, what these systems do really, really good is find connections. Find connections that we would never be able to do. We find correlations, but we do not necessarily find causation, right? The system is excellent in seeing that one set of criteria correlates to another. For instance, if you're a dog owner, it might for some reason correlate to you being a good employee. Whereas if you're, I gave this example last week, if your retina movement is too quick, it somehow correlates to an untrustworthy person. The system discovered that there's some kind of correlation within the data that shows that. And so that's how it learns through these things. And then what the job of a data scientist and of an ethicist in AI is to try and find these weird non-human conclusions that these systems reach and clean it out, right? We have to de-bias the system. We want it, and now we're going to talk about that in a second, about AI alignment and how we sort of try and do that, right? So aims, design, and data, these are the sources of algorithmic biases. What do we give the system to do? Like with Amazon, Do we tell it to find the best candidate? Do we tell it to find the candidate that most resembles the ones I have now? The design, what kind of outputs do I allow the system to have? Is a smiley face the number 6? That's how the system sees it. And the data. The data, that is everything in the world of AI. And there's a huge ethical question when it comes to data. Do I want my data to represent the world as it is? Or do I want the data to represent the world as I want it to be? And think about that distinction when we're thinking about the ethics of AI and algorithmic decision making. If I want the data to represent the world as it is, the world as it is terrible. There are a lot of problems in the world. The system would just ingest that and learn that. But if I want the data to represent the world as it should be, well, I have to answer that question. How should the world be? That's toughy. Good. So there is this question or this notion in the world of Silicon Valley that the bigger the model, the more the data, the better the answer. And we'll talk about that in a minute. I think, can't remember if it's today or next week. But we're going to talk about this idea of emergent properties, right? There's this notion, and if you look at all these corporate studies that are done at OpenAI, at Amazon, at Microsoft, they tend to come to this exact same statement or claim that says the bigger the model, the more data the model had, the better we'll become in certain things. And we can't explain why. Suddenly the model will learn to draw in a very realistic way just because I gave it more data. It has more correlation points. And so, yes, there is always this want. We want more and more data. And now you added one tiny glitch to that. You said synthetic data, right? Or you said data as we would want the world to be. And that's always the question, right? Do we give the system real life data, or do we create it on our own to make it see the world in a specific way? And then the biggest challenge is, what data do we give it? Okay, and now that leads us to the next topic. Well, first of all, as a sort of leading question, this is the biggie. This is the big question. Is algorithmic bias simply a technical problem that requires a technical solution? More data, better algorithms, more computing power. Is that the solution to algorithmic bias? And I would claim that no, that's not the solution. And that there's an underlying also ethical question or moral question that has to be addressed. And that has to do with what we were just talking about. It's not enough to capture the world as it is, because we want these systems to create good answers, not just answers. We do not want the judge that is relying on the system to ingest data that says, well, if you're a minority or you come from an impoverished neighborhood, you're more likely to commit crime. Obviously, we don't want that to be. That doesn't make sense. Or even if it does statistically make sense, it might be the wrong way we want reality to look. So let's see if it's only a technical problem. And to address that, there's this issue known as the alignment issue, the alignment problem. AI alignment is a hot word because it is a central issue behind whether these systems can be relied on in the real world. And that's why you see every single AI development company has a team working on alignment. In OpenAI, they call it the Super Alignment Project. In Microsoft, they had a different name for it. I can't remember. And in Amazon, they just published a paper from their alignment team. Every single development research institute has a team working on this problem. And let's see, why is it a problem? Well, it's actually a very ancient problem when we think about it. And this is Norbert Wiener, considered one of the fathers of AI. AI has a lot of fathers, not a lot of mothers, but unfortunately, like with philosophers, this is what we see. And today the mothers are coming out more and more and more. But traditionally, Norbert Wiener, and let's see what he says. He says to us, if we use, to achieve our purposes, a mechanical agency with whose operation we cannot interfere effectively, meaning it's too quick, it does things that we can't comprehend, too much data, right, too fast, we had better be quite sure that the purpose put into the machine is the purpose which we really desire. Remember Amazon. Make sure the system does what you want. And why is that a difficulty? And look, this was already said in 1960. So we're seeing that AI is not really a new issue here. People have been pondering the question of delegating decisions, of improving human capabilities for a long time. So the question is, what should we align AI with? We want AI to act in a certain way. What is that way? What is that core idea that's going to lead us? And of course, the first option is instructions. We want the agent, the AI system, we want the agent does what I instruct it to do. Like Weiner said, be sure that you give it the right desire or the right purpose. What I instruct it to do, it does. Now, last week we sort of saw the problem with this idea already, but the fundamental problem is known as the King Midas problem. Now, for those who don't know who King Midas was, this is a mythological story, right, from Greece, from the mythology of Greece. And King Midas, he did some good deed for one of the gods, I can't remember which one, and he was given a boon. He could request something, he could ask for a favor of the god. And what King Midas asked was that everything he touches would turn to gold. He wanted a lot of riches and power that comes with it. And so the god said, fine, go home and it shall be. But then, of course, Midas goes home and he understands that he asked for the wrong thing, because as he picks up his wine glass, it turns into gold. And as he picks up the food, it turns into gold. And lastly, as he touches his beautiful daughter and gives her a hug, she turns into a golden statue. So he got what he wanted, well, what he asked for, and not what he wanted exactly. And this is a lesson for us in AI, right? AI does exactly what it is told to do, but we often don't know or can't explain properly what we want it to do. And remember, last week we talked about these examples of extreme cases in which AI systems try and do the wrong thing, right? Detecting cancer, trying to solve cancer by infecting everyone with cancer and then testing on them different drugs. Maximizing paperclips is the classic sort of example, and then the AI system tries to maximize the production of paperclips by harvesting human beings into paperclips, right? Again, these are thought experiments to see that what you ask for is not always what you want. You want some kind of limitation. So instructions are problematic because it's very hard for us to give proper instructions to the system so that it does exactly what we would want it to do. So instructions won't work. What about expressed intentions? Okay, the agent does what I intend it to do, right? Not what I gave it the instructions to do. Well, let's see if that can work. Well, we intended here to find the best candidate, right? But what does it mean to find the best person for the job? Can I articulate that precisely? Will the system come to the same conclusion as me? Can I exactly say the precise criteria for what it means to be an excellent candidate or an excellent employee? Well, I intended to find the best employee, and perhaps what I got was the best employee according to how the system learned, but it was biased against women. So my expressed intentions can also be problematic, right? They can also not lead to the way. What about ChatGPT? What if my expressed intention is to commit suicide? Should ChatGPT instruct me on how is the most efficient way to do that? Is that okay? Do we want the AI system to do this? What if I want to create a chemical weapon or a biological weapon? Should ChatGPT teach me how to do that? It's not so hard, can it? That's my expressed intention. Do I want it? Well, we often have very bad intentions. We don't want the system to enable those. So that's a problem also. So if intentions won't work, perhaps revealed preferences. Now we're back into the realm of the behavioral scientist, the economist, right? The agent does what my behavior reveals that I prefer. So in this case, I won't tell the AI system what to do. I'll let the AI system learn how the world works, explore how we behave in given situations, and let it use its calculating capabilities to understand what is the right thing that I actually want to happen. So it'll come to the conclusion because we are terrible at giving it good instructions. We just saw. But there's also something of a problem here. Well, we see it already today, right? Spotify, Netflix, Amazon, they're excellent at sort of tracking what we prefer. They suggest us what to buy, they suggest us what movie we want to see next. Maybe it's not the best all the time, but it's improving. And oftentimes it'll give you spot on recommendations to the point where, you know, often people think that there's someone listening to them because they talk about something and suddenly they go on Facebook and they see ads for that. Has that ever happened to you? Happens all the time, right? These systems are really smart, okay? And we're not being spied on constantly by the advertising agency. So there's been no proof of that, at least. Maybe I don't know about it, but it's more predictive capability. Let the system see and learn our behavior, and it will be able to predict what is the thing we want and need. But again, here's an example of this happening today. This is known as a personalized patient preference predictor. And this is an article, we'll be talking about that next week when we talk about medical AI. Can we predict the preference of a comatose patient? Should we pull the plug or not? Are preferences stable enough that we can say this is what you would have chosen? And this is what these AI systems are being taught to do. This is a real life product, right? It's being developed, it's being researched, that we can use these as better proxies than your family. If today the power is with your parents, your loved ones, your siblings, whatever, they're thinking maybe it's more just, maybe it's more accurate to use an AI system to do that, to see the pattern of what you would have wanted. But here's the problem that we might face here. Well, our revealed preferences can often be quite bad, just like our intentions. What if this is my preference, right? To steal the crown jewels. What if this is my preference that I learn? A famous ad, keep her where she belongs. This is a shoe ad that came out. It's a real ad. Is that my revealed preference for women? Should the AI system learn that? Maybe not so good. Maybe not so nice. So there's a problem with revealed preferences as well. The problem has to do with this notion known as RLHF, reinforcement learning by human feedback. This is a very, very popular alignment tool used today in order to ensure that the AI system is not giving us bad advice or bad answers. A lot of people see the types of replies that ChatGPT is giving and ranks it as good or bad, gives it feedback. Is this what I would have wanted to hear or not? And once we have a significant amount of feedback, the system sort of learns, internalizes what is a good response and what is a bad response. And it's very, very successful. Next week, I'm going to show a few examples that I generated with ChatGPT, which I thought were excellent. And I mean, these systems are incredible. I'm talking about the ethics of AI, but I love these AI systems and what they're achieving. It's amazing. And yet it's on the basis of this type of human feedback. And what is the problem with human feedback? That it's empirically informed. It brings us back to the question that we started with. Do we want the system to learn the world as it is or as it should be?